Okay, I think we should start. Hello, everybody, and welcome to the 8th edition of the 160 Open Lecture. This time the topic is on Next Generation MIMO, and we have some very excellent speakers gathered today. So let me introduce first I'm going to explain some rules. So first, I have to mention that this session will be recorded and published on the 160 website. So we're staying here in the webinar. You agree on these conditions. Then you are welcome to post questions and comments in the chat. There's a dedicated question and answer chat area in the bottom of the meeting tool, and our speakers will do their best to address your questions. And if you experience any technical issues, then please contact our host. So let me introduce the first speaker. This is Giuseppe Caire. Giuseppe received a bachelor's degree in electrical engineering from the Polytechnic University of Turin in 1990, a master's degree in electrical engineering from Princeton University in 1992, and a PhD from the Polytechnic University of Turin in 1994. He is currently an Alexander von Humboldt Professor at the Faculty of Electrical Engineering and Computer Science at the Technical University of Berlin, Germany. Since 2003, Giuseppe has received many awards and prizes for his outstanding contributions to wireless communications and information theory, more than I can list here today. And he has been a fellow of the IEEE since 2005. He has served on the board of governors of the IEEE Information Theory Society from 2004 to 2007, and as an officer from 2008 to 2013. He was president of the IEEE Information Theory Society in 2011. His main research interests are in the field of communication theory, information theory, and channel and source coding, with a particular focus on wireless communications. Giuseppe, thank you so much for coming today, and please start with your presentation.
Thank you very much, Martin, and thank you for the invitation. So I will share my slides. I hope you can see it. So, yes. Well, in the spirit of MIMO and perspective in MIMO, I will focus today on two aspects of so-called self-free user-centric scalable massive MIMO networks, in particular fairness scheduling and fronthaul optimizations. So first of all, what are these type of networks? Well, the idea of joint processing of distributed antennas dates back to really quite a bit. Paper by Weiner in 1994 already considered the joint processing of all possible antennas in the uplink and basically derived the capacity region of this sort of multi-access channel. Many years later, the problem of the downlink was cracked, starting by from some work by myself and Shlomo Shammai, and then at the end completely closed by the famous paper by Weingart and Steinberg and Shammai in 2006. This is a famous vector Gaussian broadcast channel. Nice result. However, so the idea is that instead of having a cellular system with the cells, basically we could have just a giant MIMO system. But this idea is a little bit naive. Some attempts have been made also in practice. The famous comp schemes, not so successful because it was applied maybe not in the right setting for systems that were designed as cellular, so the benefit of cooperation was not so evident. And as a matter of fact, the massive MIMO with the per-site non-cooperative processing has taken over and has become a dominating approach in current cellular systems. One has also to say that the so-called cloud run or is a step in this direction, where basically antennas can be virtualized and distributed, but still somehow the structure is the structure of a base station. Albeit with distributed antennas, we still have boundaries. And this is not user-centric, so the cluster of antennas is defined by the infrastructure, is not defined by where the user is, right? So also as a motivating scenario, let's consider, classical or say not so high frequencies, let's say essentially FR1 and maybe FR3. Standardized for 6G, where essentially all digital processing is probably the way to go with the standard TDD reciprocity. So in a certain sense, channels are estimated from uplink pilots, and then they are used whether in the uplink or in the downlink. And this is an example of a scenario for this type of cell-free networks. So campus networks, super high spectral efficiency, super dense environments where it's extremely challenging for conventional systems to reach good performances. So it's really, in my view at least, it's not really a say substitute for cellular as it is in rural areas, not highly dense areas. Cellular and massive MIMO with per site processing is far sufficient, but in certain applications, especially campus, industrial campus, and super dense environment, it is definitely an attractive idea. So basically, the idea of these networks that have been studied a lot lately, in particular by Emil, by the next speaker, is one of the names in this area. But the idea is that every user has its own user-centric cluster of antennas, and is so jointly processed by these antennas. So this has some interesting implications. For example, suppose here we have the cluster of user K, so user K is here, but then user K will move. As the user K moves, its cluster should be able to follow him. But following, so basically there is a mechanism of enrollment and release or dismissal of radio units to the cluster, such that the user is always in the center of its own cluster. But this means that at some point the cluster will be processed by some edge computer, so-called decentralized unit, and this means that the traffic needs to be routed here. But as the cluster moves, this processing unit will be farther and farther from the cluster, which means that this function that implements the cluster processor must be able to migrate to another edge computer. And this is actually very good. It is like a perfect match with, on one side, the so-called disaggregated architecture, so the radio units and the decentralized units, and with the trend of implementing the at least the, say, upper PHY and upper protocols. It has so-called software-defined virtual network functions, such that instead of being just a piece of hardware like a blade in a base station that they decode one user and that's it, this is essentially some piece of software that runs on general-purpose machines like GPUs and CPUs and can migrate. So this is the general picture that I have. So an important thing here is the concept of scalability. So scalability is when essentially is like this. Imagine a network in a certain area. Imagine a certain given density of radio units, a density of decentralized units, and a density of user equipment. Now, as so the network is scalable if as the area of the network grows to infinity, so all these nodes, the number of all these nodes grows to infinity, still the load at every frontal link and the rate at any node in the network and the computational load at any node in the network remains finite. Otherwise, if we have just a single giant processor that processes an infinity of antennas, clearly you have to convey a ridiculously large traffic to this processor, and the computation say the computation required in this processor will blow up to infinity. So this is the context. So in this context, we have studied fairness scaling. So what is fairness scaling? So think about the following experiment. We have a simple network with 12 radio units, M antennas per radio units, resource blocks of 200 symbols, and 20 dimensions per resource block for piloting, for so-called SRS. Whatever sounding reference signals to estimate the channels basically. Most of the literature in this area has been focused on the massive MIMO regime, the regime where the combined number of antennas, so the number of radio units times number of antenna per radio unit, is much larger than the number of users. So essentially, has always plotted, these ergodic rate distributions in this regime. But this regime is not very interesting because, in fact, we would like to load the network much more. And what happens if you keep loading the network and without doing any special countermeasure, simply serve more and more users? Well, it happens that the spectral efficiency grows and at some point saturates, and at some point may even decrease a little bit. That's a typical example of congestion. In addition, what happened to the per user rate? The per user rate going from, say, serving 10 users, 40 users, 100 users, although we still see here that the spectral efficiency kind of grow and reaches this maximum, the spectral efficiency per user collapses. We see that if I serve 10 users here, I can have like a median rate of about 3 bits per second per hertz. If I go to 40, I have only 2. If I go to 100, this collapses to less than 1. So basically, there is a low diminishing return. Some spectral efficiency increases, but flattens out, and then it may even go into some form of congestion, and the per user rate crumbles. So in the real world, actually, we are always in this regime. The number of users is always much larger than the number of antennas. The example of before, we have 20 radio units, 10 antennas per radio unit, 200 antennas, 10,000 users. So how this can be done? Well, clearly, this means that we need to scale the users over the time frequency resource such that we have a magic number of active users at on every resource block, and these are the users that I can plug in spatial multiplexing, but I need to scale the users over time and frequency, which means that the ergodic rates per user in this regime are actually quite irrelevant, because what is meaningful here are throughput rates. Throughput rates is not only the spectral efficiency, but also the airtime at which a user can use the channel. In particular, because the scaling scales in relatively small blocks, and we have delay requirement, we need to decode block by block. So in fact, outage rates are more relevant than ergodic rates. So we want to look at this problem where we have effectively some physical layer that produces an achievable rate on the spot on a given block, but the matter of the fact is that at the end, we are interested in the service rate. So when a user is in the active set is the set of users that is scheduled at that time, then it's going to get something which is a random variable, which is essentially the scheduled rate times the indicator function if the rate is achievable for that slot. So it's less than the, say, the mutual information that I can achieve on a single slot. And otherwise, the service rate is 0. If the user is not scheduled, then it's 0. Then the problem of fairness scheduling is the following. We can define these long-term average rates, which I call throughput rates. And the problem is maximize a desired network utility function of the throughput rates, subject to that the throughput rates are feasible. So they are in the region of achievable throughput rates. In general, for well-known network utility functions, they're typically concave and component-wise non-decreasing. So what happens here is that this problem is always a convex problem, because by definition, because throughput rates are obtained by time sharing, then necessarily this is a convex set. However, the analytical description of this convex set is extremely complicated. It's not a polytope in general, so this problem is generally extremely difficult to solve. So what do we do? Well, actually, what we do, let me just cut short, we use a scheduling algorithm. There is this nice theory of Lyapunov drift plus penalty that essentially is guaranteed to make the system operate very close to the maximum of a desired network utility function, provided that one can update weights. The weights are called virtual queues, but they have nothing to do with actual transmission queues. This is very similar to proportional fairness scheduling already in the third generation, where basically there is like an iterative way of computing priority weights that give priority to the users. So I will not go into the analytical details here because I don't have time, but let me say that the key point here, the key point is that at every point in time, the scheduler solves a weighted sum rate maximization where these weights are iteratively computed over time, and these weights somehow push the system to operate at this point in the throughput region that maximizes the utility. So the key point is solving the weighted sum rate maximization. And this is a hard problem. So of course we do it in a heuristic way. So basically, first of all, we assume that the users, the statistics of the mutual information that the users see does not really depend on which user are scheduled, but only on, say, the ensemble, because it's a large system, and on their own channel statistics. So we have this sort of stochastic decoupling of the problem. Now, this is not entirely true. It's true only if users are not in hard conflict, in the sense that do not have a hard pilot contamination problem. So we define a conflict graph that spots the hard pilot contamination problem. So user sharing the same pilot, because we have a large number of users. We have 10,000 users, but we have only 20 pilot dimensions. So there is a lot of users sharing the same pilot. So we do not want to pick users that share the same pilot. They are too close to each other. So given this conflict graph, then at the end, the weighted sum rate maximization can be written as a integer linear program that can be solved even for large dimension with say standard solvers. So here is an example. We have consider like a sport arena, so 200 by 200 square meters, 20 radio units with 10 antenna each, so a 200 antenna in total, a bandwidth of 60 megahertz, resource blocks of 200 symbols with 20 dimension per resource block for sounding pilots in the uplink. every resource block spans 12 subcarrier with this spacing. So basically, we are going to allocate our 10,000 users over the resource, f channels in frequency. So it turns out that if f is equal to 1, we can have 80 parallel channels in frequency, and so we have only 125 users per sub-channel, but this has very little frequency diversity. If f is equal to 8, we have 1,000 users per sub-channel. Everything else is pretty standard. We target to serve on every sub-channel, serve a number of active users, which is half of the total number of antennas. So what happens here is that here you can see the scheduler. So if we don't do anything and we just do max sum rate, we end up with these curve. This is average throughput, and we see that this has a step at 0. So almost half of the users get 0 rate. Those are the users that are naturally disadvantaged, and the system that maximizes sum rate will just simply not serve them. Clearly, this is not an acceptable solution because these users pay their subscription exactly as everybody else. They want to be served. So if we impose proportional fairness scheduling, we get this purple curve. If we impose so-called max-min or hard fairness scheduling, we have this, which is essentially put all the users, it's just a step function, so it essentially puts all the users at the same, essentially at the same throughput. And interestingly, here we see that, for example, with proportional fairness scheduling, the median rate, median throughput is something like almost like a 900 megabit per second, no, sorry, 900 kilobit per second, so almost one megabit per second. And these are real numbers. So these are really the 10,000 users achieve almost 1 megabit per second of good throughput. Is not the instantaneous rate on a single slot, is average over time. And I think that this is quite interesting, that a system like this can actually serve 10,000 users at 1 megabit per second of good put. This is another result that simply shows that there is a trade-off between the frequency diversity. So if we make the channels larger, we have a larger frequency diversity, so we get a little bit of better hardening of the multiple information, so the outage rate becomes a little bit better, but the complexity of the scheduler is higher because, for example, we have to schedule over many more users with better rates, etc., etc. So I think I'm really quite tight in time, so I will spend just a couple of words on the other problem that we have looked at, which is the fronthaul optimization. So going back to the beginning, we have this scenario where cluster processors are allocated to DUs in a dynamic way, and for example, this user, say user 2, is served by this base station, say this antenna unit, this antenna unit, and this antenna unit, but this cluster processor is here. So it means that the received signal in the uplink must be routed for this relative to this user, must be routed here because it's needed here by this decoding function. And at the same time, the information bits that will be being formed or pre-coded to these users must be basically routed from this unit to here, and then here, and then here in the other direction. So what is the problem? The problem is that given a certain association of users to clusters, so user-centric clusters, we want to place the cluster processor into the DUs and calculate the flows through the fronthaul such that we minimize the fronthaul bottleneck. So we run a classical load balancing problem. Load balancing problems are always calculate the flows such that the load, the maximum over the links of the load is minimized. So it's a min-max problem where we want to minimize the maximum load over all the links. And these two must be done jointly, because it's clear that if this cluster process were allocated here, well, the flows and the requirements of routing would change. So what happens is that, again, important to notice that we have in the uplink direction, we have a multiple unicast. Every radio unit produces a local observation, a local combining for all the users that it is serving, and then these are actually information sources that have to be routed through the fronthaul to the destination, which is the cluster processor, the DU hosting the corresponding cluster processor. In the downlink direction, so from DU to RUs, we have a multiple multicast, because as you have seen here, the information bits for user 2 must be routed here, here, and here. So this is a multicast problem. And then, of course, we have many of these flows, one per user. So we have these two situations. It is important to connect the rate on the fronthaul and the rate on the physical, say on air, so the physical layer rate to the users. And in particular, we have that every radio unit produces an observation. So a radio unit L, user K, produces an observation that has a certain energy, a certain energy per symbol. And so we quantize that, and it turns out that if we fix a common level of distortion in the quantization of the fronthaul, these are exactly the bit per symbol that we need to pump through the fronthaul. So this is the rate of the source corresponding to user K received at the radio unit L. And in addition, we have this nice additive noise representation where, again, all these coefficient alpha and the variance of this quantization error are all determined by this level of distortion. So what we propose is to use essentially what is called the reverse water filling. So instead of fixing the quantization bits, that doesn't make any sense, we fix the quantization distortion, which means that if a radio unit receives a very weak signal for a given user, well, this ratio will be less than 1, and so we dedicate 0 bits. If a radio unit is very relevant for that user, then this ratio will be large, and then we dedicate a number of bits. For the other direction, in fact, the best thing to do is to send directly the information bits, not the pre-coded symbols, not the OFDM symbols, the information bits to the radio units, and let the radio units do everything else, because the information bits are uncompressible and everything else is redundant. So, and this, by the way, corresponds to the so-called 7.2 splits in one direction, while here we have the 7.3 split. So, you know, the beauty of academic research is that we are much more free to do things, and this turns out to be the best thing we can. So at the end, basically, when we define these allocation variables to allocate the cluster processors to DUs, the whole problem eventually the joint load balancing and resource allocation problem becomes a mixed integer linear program that can also be efficiently solved. And here is just an example, for example, for a given topology. So we have this is the say air interface topology, and here is the fronthaul topology, and then we can essentially is the same system as before. These parameters are identical as before. So what we see here, and then I conclude, is the following: is that of course the quantization in the frontal is only relevant in the so-called uplink direction. So from the radio units to the decentralized units. There is no need to quantize in the other direction because you just send the information bits. In practice, you will just send the labels of your QAM symbols in the frequency domain. So we see here that the spectral efficiency is essentially flat with respect to D. The only effect is that, well, it's in the cluster definition because the cluster is some radio unit is too weak, so it gets quantized to 0. Then basically is also not using in the downlink. In contrast, we see here that the spectral efficiency, even for relatively large quantity, this is the minimum energy of a signal received by a radio unit for a given user in its cluster. So when this ratio is larger than 1, it means that this weak observation will be simply thrown away. And yet, we see here that the variation in spectral efficiency is relatively reduced. In contrast, we see here that the variation in frontal load is basically 100%. So in other words, using coarse quantization reduces the uplink spectral efficiency by, I don't know, a small percentage, so from 98 bit per second per hertz to 106 bit per second per hertz is, I don't know, is really a fractional percentage, but in contrast, it reduces the frontal load by 100% from 400 to 200. So basically the bottom line of this study is that say aggressive quantization in the uplink direction is good. By the way, quantization in the frontal has nothing to do with quantization in the front end. You can have your 12 bits A to D converters in the radio units, do all the channel estimation, the FFTs, almost if it was in floating point. And after you have done local combining, then you quantize to compress to send a low rate in the frontal. There is no connection between the two, no logical connection. There is no reason actually that this should be. In terms of frontal load, the bottleneck is the uplink, but this is good news because these results are for balanced traffic. So one slot. So say 50% of the slots are uplink and 50% are downlink. As a matter of fact, typically the duty cycle of the downlink is much larger. So basically, the bottleneck is in the uplink, but we use the reweighted by the duty cycle in the uplink downlink. This means that we can actually achieve much less say load in the frontal. And the fourth point I want to make is that in order to exploit these, it is beneficial to have so-called half duplex frontal links. So basically links that can transmit in both directions. So basically we can say flexibly allocate the throughput between uplink and downlink direction. If we have like how you do full duplex in practice, you have two links, two cables, two fiber optical links, and in this case you cannot transfer capacity from one to the other. So this concludes what I wanted to say, and I'll be happy to answer some questions.
Thank you so much, Giuseppe, for the great presentation. That was very interesting. We are already quite over time. I would suggest that you go to the question and answer session and answer the questions online, because now we need to move on. Otherwise, we will run out of our schedule. So thanks so much. So this was very interesting, emphasizing the importance of scheduling for MIMO systems. Now we will have our next presentation. I'm sharing my screen. So now moving on to the next talk, let me introduce our next speaker. So can you see the screen? Yes. Okay, this is Emil Björnsson. Emil Björnsson is a professor of wireless communication at the KTH Royal Institute of Technology, Stockholm. He is an IEEE Fellow, a Digital Futures Fellow, and a Wallenberg Academy Fellow. He has a podcast and a YouTube channel called Wireless Future, and his research focuses on multi-antenna communications and radio resource management using methods from communication theory, signal processing, and machine learning. He has authored 4 textbooks and published much simulation code. He also has won a lot of prizes and awards. Yeah, Emil, thank you so much for coming today, and please start with your presentation.
Thank you for the kind invitation. And let's see, now did I share the right screen? There it is.
Yes.
Great. So I'm very happy to be here and see that so many people are in the audience. So I will talk about one of my favorite topics these days, which has to do with the radiative near field, which is sort of challenging how you have been taught to understand wave propagation and how you can do MIMO communications. So I've been really keen on trying to understand this in the last few years. And today I will talk about how one can utilize such properties to do spatial multiplexing from a few different perspectives. So the starting point for this is, of course, that we always need to evolve mobile communication networks because the network capacity is growing. From a demand perspective, we have this kind of numbers that are showing how the traffic is growing over the years, and now we are in 2024 and traffic will continue to grow. Maybe not as quickly as it did a few years ago. We had some years in the beginning of the 4G era where the traffic was doubling every year. Then nowadays it is more like growing at the same pace as the traffic on the internet in general, because wireless is just such a natural part of our lives. So it's not like we're moving more traffic over to wireless, it just grows in the same way. But the main point is that the demand for wireless connectivity is growing all the time, which means that we need to also evolve the supply of connectivity and of capacity in our networks. And there we have this kind of basic formula that per access point, if we have a cellular network, the number of bits per second is governed by a channel capacity, which is if there would be some kind of typical SNR, log2 of this SNR times our bandwidth times the number of spatial layers or spatial streams that we can send at the same time at the same frequency. And this is then the formula that we can deal with. And we shouldn't expect the SNRs to grow that much in our systems. So it's typically these two factors that we can play with. So we can say in 6G, will we have more spectrum? Probably. We will assign some new frequency bands. However, the bands that people are looking into now are the centimeter bands, which are between the 5G bands at the 3.5 gigahertz and millimeter waves. And there, the amount of spectrum is not much more than we have in 5G today. Of course, we get more spectrum, but it's not like it's orders of magnitude larger, not at all. And we have seen that millimeter wave didn't take off particularly much, which is then asking the question, well, if we can't expect to make use of large amount of more bandwidth, what can we do in order to deal with the capacity growth? Well, that might be to have bigger MIMO, more spatial layers. And what would that entail? Well, that is one of the presentations really is about here. And to some extent, just adding more antennas would mean, okay, you have more number of layers, you have more dimension in your matrices, fine, everything else remains the same. But that is not necessarily what is going to happen. And here is an illustration of this. So say that you have an antenna array with a particular size, L times H, so the length and height of this array. Then when you are radiating the signals in a particular direction, when you're just a few wavelengths away, you can see how the wavefronts here are spherical. And then when you move some 1,000 wavelengths away, or actually closer than that, when you zoom in at a particular piece of the wavefront, it will look more or less flat. So this is how a spherical wave looks approximately flat or planar at the typical distances that we're considering communications. And this is where we have been used to divide things up into different ranges. The far field regime, which is traditional propagation scenario, where you are sufficiently far away to mainly observe these planar waves. And close to the array, when people hear the term near field, they usually think about what is known as the reactive near field. These are not the waves that are leaving the array, but it is the electromagnetic wave that are staying around the transmitter. And this is what you're using for near field communication, or NFC, when you're making mobile payments, for example. But this is not what we will be talking about today, but an interval in between, which is known as the radiative near field. And when the receiving user is at a distance smaller than the Fraunhofer distance, also known as the Rayleigh distance, well, then you will be in this radiative near field. And that the expression is 2 times L square H square, so it's essentially diagonal here squared, divided with the wavelength. So we can see that there are 2 ways of making this boundary moving further away so that the radiative near field expands. And this is to make the array physically larger and to go up in frequency so the wavelength shrinks. Both of these effects will change things. So what could be the implications of being in the radiative near field? Well, traditionally, with the 5G antenna arrays that we have today, the users are typically far away. We have the Fraunhofer distance somewhere, and the users are much further away. And then when we transmit to them, we transmit beams. In a line of sight dominant scenario, this is how it's going to look like. 1 beam for this user, 1 beam for this user. And these beams are often drawn as if they start at the base station, but they don't. They start somewhere slightly before the Fraunhofer distance. Before that, the wavefronts are kind of chaotic, but then here it starts to take the form, and then they continue all the way towards infinity. If we now would increase the size of this array, and we create something we call extremely large aperture arrays, there are a number of different names. People call it XL MIMO, for example. Well, the first thing that will happen is that the Fraunhofer distance becomes substantially larger. So this is then the new value here. So the same far field users, they are actually still in the far field, but their beams are not starting until you are further away. And because the array is bigger, the beam width also shrinks. So around them over here, they are not as wide as they were up here. But then we see that there is a large area here. This is the radiative near field, where these beams haven't started to take the shape yet. So the signals are not very strong. They are spread out there. And this is where we can do new things. For example, we can serve users at different distances. So if you focus the signals with traditional beamforming, you figure out, okay, from my different antennas, what is the phase shift to this particular location where the user is? Okay, let's match to that one so that we get coherent beamforming. Then the area where the beam will be strong will not be like a cone of this kind, but it will be an area around the receiver. And this allows us to not only distinguish between users served in different angles, but also use this distance metrics to discriminate users at different depths. So we can serve all of these 4 users at the same time, at the same frequency, and separate them both in angle and in depth. And this would allow us to serve users in different ways at location that we were not able to do before. In addition, when the array becomes bigger, the beam width also shrinks. So some users might have a beam that is so narrow that the device is bigger than the beam width. And in this case, we can even send multiple data streams in a line of sight scenario to the same device. So with the large antenna arrays, more narrow beams, finite depth, if you are serving in the radiative near field, and this can be utilized for improved spatial multiplexing. So to give you a sense of then what could the Fraunhofer distance be? Well, a typical antenna array today, maybe it's this 1 by 1 meter size, the 3 gigahertz band, and then the Fraunhofer distance is 40 meters. And you typically deploy base stations on some elevated places. So 40 meters, most users are much further away from that. To some extent, you're not supposed to be closer than some 20, 30 meters away from a base station for safety reasons. If you keep the same size of your array and go up to 30 gigahertz, well, then since you divide with the wavelength in the Fraunhofer distance expression, you expand this up to 400 meters. And if you make the array bigger, so you spread them out over, for example, a building, then if it's 10 by 10 meters, you can make the Fraunhofer distance 4 kilometers. So then obviously you will be, everything that you will cover with this base station will be in the radiative near field. So with a bigger array or higher carrier frequency, we will expand the near field and make use of these kind of effects. So what implications might that have? Well, that is what I talk about first from a multi-user MIMO perspective, and then more about the single-user MIMO case. So when it comes to serving many users and trying to exploit this depth, the thing is that if you have, say, a base station with n antennas and every user just have one antenna, the channel to this user is a vector of length n. And this vector will, of course, belong to the space of all n-dimensional vectors. But there will be a subset of all of those vectors that are physically possible channel vectors. And the dimension of these ones is known as the degrees of freedom. And also, even if you have a particular dimension, it doesn't mean that all possible vectors are, the dimensional subset can be much smaller than n. And also the likelihood of having particular channels in the practical environment can also change depending on what propagation environment you have. So here's a simulation example showing what impact this might have. So we considered a 1 by half a meter array at 30 gigahertz. We fill it with a lot of antennas. And in this case, the Fraunhofer distance becomes 250 meters. We were dropping users uniformly at random up to 500 meters. We have a mix of near field and far field effects. And we keep dropping more and more users and keeping everything else fixed here. And here's a simulation of the sum spectral efficiency in bits per second and hertz. So some kind of sum capacity that you will get depending on how many users you have. We start with 10 users, there's logarithmic scale. So here's 100, and here is 1,000 users. We assume perfect CSI. We assume that you just use the best kind of MIMO things from for example, my recent textbook here. And the main thing is that the blue curve is if we are capturing both the near and far field effects in our channel vectors. And the red curve is if we are approximate the channels as if this were just array response vectors for the far field. So we neglect the existence of near field effects. And what you can see is that when you have some 10 sub users here, well, your array can discriminate between them very well. And it doesn't matter if you have the possibility of using the distance or depth domain as well, the performance is roughly the same. But as you keep loading the system, this extra richness that the channel is getting, because you both see angles and distances, this is helping us to distinguish between users. The capacity keeps growing with the number of users, while if you only have far field phenomenon, you see that it saturates and starts to go down. So this is one of the important things that is happening here in the near field. We can serve more users in practical environments. The maximum number of users will still be sort of equal to the number of antennas here, but if you just drop them randomly, the richness of your channels becomes higher in the near field, and that is providing you the possibility of serving more users. So how many users can you actually serve from a base station perspective? There is the spatial degrees of freedom that is giving you a limit on how many spatial layers that you can separate, for example, using zero forcing and other methods, because the channel rank is given by this number. And if you have a planar array, which is size h times L, then there is a formula that has been proved a number of times over the years that is pi times the L times h, which is the area, divided with the wavelength squared. So this is essentially how many antennas you would get with lambda over 2 spacing, but you lose a little bit because the angles horizontally and the angles vertically are not independent of each other. But this is the formula. Let's do some math. Here's a typical base station in the 5G case. It's half a meter by 0.7 meters, this typical antenna array. If you do the math for this case for the 3 gigahertz band, well, you get a 110 degrees of freedom. And today we are typically putting in 64 antennas here. You could squeeze in more here. Theoretically, you can get a little bit more into this box, but it usually have not lambda/2 spacing, but a little bit more. But in this case, with the sizes here, users will be in the far field. You will see beams of this kind. If you would instead spread out antennas over the facade of the building here and make it 10 by 30 meters big, and you do the same math computations again, you will see that you can get 100,000 degrees of freedom from such an array. So there's really not a close by limit on how many degrees of freedom or how many users a base station array could handle if you make MIMO dimensions much bigger. But the question is, of course, how many of these ones will be practically useful? And if you're serving a particular user, well, you might send multiple streams to it, but the same formula applies to that one. You take the size of that device and you do the math, and you see that at 3 gigahertz, it might only be able to obtain 3 degrees of freedom. And those ones will probably become one signal directly in front of you and then 2 from the sides. So it's not necessary that that will be mapping with what the base station like this can serve. These numbers are sort of just upper bounds on how many streams you can get in a very rich propagation environment, but not necessarily what we can achieve in practice. If we would like to try to squeeze up the degrees of freedom even more, we can use dual polarization. We're actually using that all the time, both in base station and devices today. So all the numbers are provided here should actually be doubled. And if you go up in frequency from 3 to 30 gigahertz, well, you shrink the wavelength by a factor of 10. And since you have divided by lambda square here, you would get 100 times more degrees of freedom. So there are a lot of spatial degrees of freedom available. The question is what you can utilize them for. So let's take a closer look at that. Here is a line of sight situation for one device, but we will see later that it might be, in the way I'm describing here, more for a backhaul link between 2 big MIMO arrays. But anyway, we have decided 2 locations which are distance d apart from them. You have m antennas in a uniform linear array fashion on both sides, and there is a spacing delta between them. And then the channel between them will be represented by a channel matrix, m cross n. And it's a free space line of sight scenario, so you only get the direct path between any pair of antennas. And to some extent, the propagation environment is defined by that. There is a distance. I said it was free space line of sight, so that's it. But you can still engineer the channel by varying the spacing between the antennas. And this is something that people started looking at already some 10 years ago. So the problem would then be to optimize the spacing delta to maximize the MIMO capacity. And MIMO, from the point of sending multiple data streams, is only useful if you have high enough SNRs you would like to put power on multiple spatial layers, so multiple singular values of your matrix. So we consider a high SNR scenario, and in this scenario, the best thing you can have is if all the singular values of your matrix H are equal. Then you will maximize the high SNR capacity. So the solution to such a problem would be to try to analytically work with this expression. You can take the spherical wave expressions, you can use a parabolic approximation of them, and enforce that the columns of H should be orthogonal to each other. And that will then, if you have those conditions satisfied, you will get m equal singular values. And there is a paper who started doing that, or a couple of them some 10 years ago. We recently redid this for uniform planar arrays with dual polarization in a paper which is currently under review. And what you realize then, if you have 2 matching uniform planar array and you can play with the spacing between the antennas, we have MH antennas horizontally and MV antennas vertically, there is an optimal spacing that have a nice closed form expression. You want the spacing to be the distance between the array times the wavelength divided with the number of antennas that you're going to place in that dimension, and then you pull the square root of it. and then the same kind of formula horizontally. So these two formulas are independent of each other. The design horizontally and vertically doesn't depend on each other. So if you just put out the antennas in that way, dependent on how many you want, what is the propagation distance, what is your wavelength, you can maximize your MIMO capacity. The question would then be, okay, so how big does this array become? Well, if you horizontally want to put out MH antennas, we take that value, we multiply with the spacing between them, and then we know what is the horizontal width. Then you vertically do the same thing. You have MV antennas, you take the spacing between them, you multiply that together, and you do the math. You introduce M as the total number of antennas, so MH times MV, and this is our formula. Distance times wavelength times the square root of the number of antennas. If you say, well, I'm deploying this, I actually are space constrained. The area is given to me, and I can deploy as many antennas as I want, but only in that area. Well, then we can take this equation and solve for M instead, for a given area. And this is the formula to get. The number of antennas that you can squeeze in and maximize your MIMO capacity is equal to the area squared divided with the distance between them divided by lambda squared. And we see once again how this lambda square behavior shows up. The larger the carrier frequency, the smaller is the wavelength, the more antennas we can squeeze in. And in this case, we will get M degrees of freedom times 2 because dual polarization, and we have equal singular values. So it's really an ideal MIMO channel. And the values of the singular values here is also independent of the number of antennas, because we're assuming in that one antenna from each side here, there is no interference between them. We essentially put the antennas so they are in each other's nulls if we do receive beamforming. If we compare this formula with the formula they had before, which was like sort of pi times the area of your array divided by lambda square, you will figure out that this is much smaller than 1. So if you deploy a transmitter and receiver 2 places and would like to get as high MIMO rank as possible between them, it will only capture a small fraction of what an array could actually get in general. This is for the single user MIMO case. You can also serve users in other direction at the same time, as long as they are very different from these ones. Okay, so we have seen that there is some connection here between the number of antennas and our carrier frequency or wavelength. So let's take a closer look at that as well. We have a capacity, which is the bandwidth, as I said before. Then we have the number of layers that I had from the beginning. And now it's 2N, dual polarization, and we can put in two M antennas, and we had this formula that we computed, which depends on the wavelength. Then we have log 2 or 1 plus the received power per antenna, and we have we divide it by 2 because we need to split it over our 2 polarizations, and then we have here our noise power in total. And the interesting thing then is that we get more spatial degrees of freedom as we are increasing the carrier frequency, the wavelength shrinks. But what about our received signal power? Will that one also depend on the wavelength? Yes, if we assume isotropic antennas, then for every antenna we have, the area of such an antenna is proportional to the wavelength squared. So if we go up in frequency, so the wavelength shrink, well, we get more antennas, but the area shrinks very rapidly. And that is telling us that the received power per antenna is the transmit power times this classical formula, which is shrinking with the wavelength. So if you put this into the expression here, and you see what happens when I let the wavelength becomes bigger, wavelength becomes smaller and smaller, so the frequency goes up towards millimeter wave, terahertz, and so on. Well, you will be converging to a particular constant value. So there is an upper bound on what you can get out of this when you go up in frequency and get more spatial layers. But there is nothing that requires us to use isotropic antennas. If these are deployed to point towards each other, we can actually design other kinds of antennas as well. So let's consider some directive antennas. Each antenna have at the transmitter have a certain area AT, and at the receiver an area AR. We assume that if we multiply them together, they are if you multiply this with itself, you get lambda square. Now we say, lambda to the power of 4. Now we say that it goes to lambda to the power of 4 minus something that lies between 0 and 2, but not including 0. So we are not in this case. Then the received power will instead be equal to this thing here, divided by lambda square. And if you do some calculations, you will see that the capacity will now grow unboundedly as 1 over this lambda over 4 minus rho. So if you have your slightly directive antennas, as you go up in wavelengths, you can get higher and higher MIMO rank into the same area, and you can also maintain that you have a nice SNR for each of those different tracks. So here is an example of this with a numerical example. Line of sight scenario, 5 by 5 meter array. So this is really like backhaul links, but they're 80 meters apart. We have a typical 5G wavelength of some 90 megahertz. And here you can see what happens with isotropic antennas. As we go up in carrier frequency, we get higher MIMO rank, but we get less and less power or SNR per degrees of freedom. So we are converged to the upper limit. But if we have more directive antennas, we can sustain that the capacity grows with the wavelength, even if we don't use more bandwidth, just because of the higher MIMO rank, and the capacity keeps growing upwards. Same transmit power, just higher MIMO rank. So with slightly directive antennas, we get this kind of effect. The spatial degrees of freedom grows as the carrier frequency squared. The capacity grows in that kind of way as well, because it appears at the pre-log factor to the log expression. So to wrap up, we can achieve much higher capacity in 6G without actually needing more bandwidth by playing with the MIMO rank. And we can, of course, deploy larger MIMO arrays, but if we will keep increasing the carrier frequency, we can also let the capacity grow at the carrier frequency squared thanks to MIMO, which is typically faster than what you can expect by if you would go to millimeter wave or terahertz just to get more spectrum. Then typically the amount of available frequencies there, spectrum is proportional linearly to the carrier frequency. And now we have a faster scaling. The maximum degrees of freedom and also the practical ones are proportional in this way. We need to think about what kind of array we're designing, both the shape of them, what kind of antennas we're having in order to maintain the SNR, in order to make use of the degrees of freedom in an effective manner. But there are many more dimensions out there that we can utilize to get higher capacity in the future. Near field propagation effects are important and give us richer channels. We can control both angle and depth, but it's not the most important thing. It's the higher MIMO rank that's really important in the future. So I have some recent papers, both a magazine paper in the IT magazine and a recent book chapter where you can learn more about these things. Thank you.
Thanks so much, Emil. Very much liked your presentation. Thank you for this excellent presentation. Yeah, so this is an exciting area. I would have a quick question. So basically, this is about shaping and modeling the channel. So it's about array design and so on. What about the MIMO processing aspects? Will we still continue using the same algorithms and beamformers, or do we have to consider anything particular in terms of MIMO signal processing?
Right. So I think that the first spontaneous answer to that is that no, it's kind of boring. We can use exactly the same algorithms as before. But I think when you then look aboard carefully, people were really afraid that in the massive MIMO era for 5G, computational complexity would make this just impossible to do. Then it turned out that we can still do it. But if typically for regularized zero forcing computations, it's the scale with the number of antennas and number of users in such a way that if you increase both of them, you get a cubic scaling. So I think the complexity will be a real bottleneck eventually, and then we need to be redesigning our ways of doing this. So need some more algorithm. And I think channel estimation will also be a channel. There is this challenge. There's this classical thing saying that you can't estimate more channels than half of your coherence interval. And that is true in ID rarely fading channels, but possibly for in scenarios like this, you want to load the network with so many users that you run out of such resource and need to think carefully about how to do channel estimation.
Right. Yeah. So thanks again. Now moving on to the next talk. And by the way, there are a few questions in the Q&A area. So please check.
I will have a look.
So now moving on to the next talk, let me introduce our next speaker. Oh, I first need to click share. Okay, this is Jose Francisco Montserrat del Rio. He's a full professor and the vice president of the Technical University of Valencia. His research focus is on the design of future beyond 5G wireless systems and their performance assessment. He has been involved in several European projects like METIS, METIS2, 5G Common, and 5G Smart. He co-edited the Wiley book Mobile and Wireless Communications for IMT Advanced and Beyond, and the Cambridge book 5G Mobile and Wireless Communication Technology. He's a senior member of the IEEE and has published more than 60 journal papers. His current research team consists of 5 postdoctoral fellows, 8 PhD students, and Jose has served as an advisor to the European Parliament and the World Bank Group in the vehicular 5G communications. So Jose, thank you so much for coming today, and please start with your presentation.
Thanks to you, Martin. Thank you for this kind introduction. And well, for me, it's a pleasure to be here. This initiative from 1CG is remarkable. So thank you for that. I think it's important for the community to be engaged and to listen to people I like so much, I love so much as Emil and Giuseppe is also for me a pleasure. So I will talk fast because I am supposed to have only 15 minutes left, but I will be the fastest as possible to talk about a principle that you will understand super easily when you put in your brain now a thermometer of mercury and you imagine it growing up and down with your temperature. So this is the basics of the fluid antenna systems. And in fact, I did not talk with Emil before this meeting, so I did not know how was his speech, but he mentioned several things super important in the discussion we have today on the table about massive MIMO, that are basically that we need more degrees of freedom. And we need to operate in a simpler way with these degrees of freedom, and this is the basic of the continued growth that we are facing for the future 6G. So this presentation is about this. It's about introducing to you this concept of fluid antenna system as a candidate. I don't know if for 6G or for 7G, because the technology is still in an embryonic phase, and then give you some basic state-of-the-art results and challenges and opportunities, also to motivate some of you, some of the PhD that we have today connected that they can do on the research part of this. So the background is basically what Emil was explaining, and he explained super well. The 6G means in 2030 from 30 to 100 times the capacity demand we have today. The plan is to go for 100, but actually the growth that we are expecting today is more close to 30 times. But still we need to grow. And the way of growing, as he explained, required to go for massive MIMO because the amount of spectrum we have in FR3 is not allowing us to increase in these 100 times capacity demands we are talking today. And we have this scalability problem that we have been discussing today. And in fact, even if we want to go further, current systems, they don't support more than 8 multiplex users or 16 layers. And this is a limitation now of the algorithms that Martin was explaining. Is it possible to continue with our current algorithms with zero forcing, with this inversion of huge channel matrices? Actually not. We have a problem there. And the technology so far has been pointed to non-orthogonal multiple access as a solution. This is not a 5G technology. It was not included in the standards as such. But we have successive interference cancellation, a concept that was introduced in the field by Giuseppe Caire, kind of 20 years ago, SIC. But this solution that is based on multiple iterative cancellations pose also complexity on the UE side. So we don't have still the holy grail of what is going to be the solution for this 100 times capacity demand that we foresee. In fact, Emil introduced the solution and he explained it super simple that everybody can understand. But in his work, there are things that are really currently on the hot topic because we need to go into this frequency increase, into this compact of antennas to be able to grow with antennas. So is the fluid antenna system a solution for this? Maybe not in the short term. I would say that we are still in early phases, but it's true that it is a potential solution, and it's promising things that are really amazing. And the concepts, the degree of freedom that we can get from them is actually giving to us more diversity and multiplexing gains than what we understand today. It will simplify the acquisition if we are fast enough to be able to move into the ports that we will have in the future with this fluid antenna system. It will simplify the complexity of the precoding. It will remove this precoding need. And on the other hand, you need any kind of simple, and I put in on bracket simple because it's not simple at all, but you need to start inferring the interferences, managing it, and allocating these ports in an intelligent manner, which is actually a really hard problem. Here is more about the scheduling that Josep explained problem rather than a problem of precoders. So this is the concept of fluid antenna system. As I said, imagine yourself a thermometer. We are not using mercurium. We are using eutectic gallium indium, and this technology that has already 20 years because it was made by Jacob Adams in North Carolina State University, is based on a metallic fluid. So it's no longer static, it's metallic. And this has some nice properties because it's flexible. So this is an antenna that you see him manipulating. And this antenna is totally flexible and does not lose the properties. It changes a little bit the resistance and therefore the voltage of it, but you can integrate it. But not only this, you can print it easily, and it has a surface tension that can maintain this liquid fixed unless you provide something. And this something that makes the metal to move is either voltage or its temperature or its pressure. So you have to add something on top of it to be able to manipulate. And if you give enough space in a container for this metal to move, I mean, if you imagine yourself giving some space for it and you apply any kind of control of it, like for instance tension, as you are going to see, you put voltage, it will destroy the tension of it, then you will be able, as you see in the video, to move the performance of the antenna. So we have an antenna, basically, which performance as a thermometer will adapt to any kind of controller that is based on a closed loop process that allow you to make some decisions on this container, then modify the position of the liquid on the antenna. And now you have, as I said before, another degree of freedom, which is actually where your antenna is going to be placed and which is the performance of this antenna. So this gives us a new umbrella of everything. I put here the paper from Keiki Wong that I would say now is the father of the fluid antenna systems from University College London. And I like a lot this, he used to use the Bruce Lee inspired systems, be water, my friend, right? So Bruce Lee inspired antennas in the sense that they are water antennas, so they are fluid, and therefore we can play with them. So these antennas has already been manufactured, and we have some prototypes already there that we are testing, and it's based now on 3D printers, very simple, in which you have any kind of vacuum space or air container, and inside this you have any kind of metal, liquid, as I said before, this mercurium or similar liquid metal, and then you have an inlet and outlet ports in which you can either by pressure, by temperature, by voltage, or even by electromagnetic field, you can control the position of this fluid that is inside the contactor. So this, as I said, will change the characteristics of this radiator, and therefore you will have a different performance of the antenna, different pointing of the antenna, different behavior. So this is the basic of this principle of fluid antenna systems. Is it promising or not? Well, the question is, as you will see now in the picture below, if I can move it, that the antenna is elastic, as I said. So it can be integrated wherever. It can be integrated in clothes. It can be integrated in flexible phones. It can be integrated in devices that we cannot imagine today, maybe in glasses or whatever. And as you see in the video, if you manipulate this gel or this glue that you have, silicone that you have inside it, the metallic sources, what you are changing are the properties, the resistance, and therefore you increase the voltage of the system. So it's a basic principle. So now you imagine this fluid antenna into the borders of a phone, and you put on it an air chamber, and you put on it a kind of a inlet-outlet process of controlling the position of the fluid antenna, you will have different positions of the antenna, different position of the metallic element of the antenna that will change totally the pointing of your phone. So you are basically electrically controlling the performance of your phone. Or what is the same, you have an antenna with many degrees of freedom. We are talking about 100 degrees of freedom that give you this reconcavability, this dynamicity that you need to increase the capacity of your system. This is also compact, this is also lightweight, it is also easy to integrate in a system. So how we are going to play with several users in this MIMO system that we are foreseeing? In this case, what we have to play is with the position of the fluid of the elements that we have on top of these two users that you hear on left and right. They are in a different ports, the fluid elements, so being in a different port, it has a different behavior, and you have to find the position in which the signal from the red user, which is the transmission of the antenna on the right, that here you see in red, is giving to you maximum SNR for the receiver one. So you have to play with the position of the fluid of the port of the antenna until you find actually where you have the maximum. In this case, the maximum is located in this position, which corresponds to this SNR, and you have another SNR that is more or less good here. You could play also here, but of course you cannot go to this point, because if you put the fluid in this point, you will get a zero. So how this positioning of the port is integrated is the question that I said before. It's now a question of optimizing the location of the port of the antenna, because you can actually change and multiplex users through this. The second user will have a similar behavior. He will have to adapt to the position in which, in this case, the red line is maximum and the blue one is minimum. So it will be ideally a position in which you will have this perfect combination. So what is promising the fluid antenna system for MIMO? What it's saying is that, as Emil was explaining, these small degrees of freedom we experience today in MIMO antenna arrays, you can overload, you can change them thanks to the use of fluid antenna system, because actually you can put at least the same number of users as antenna ports you have in your base station. So this gives you, in the case I said before of 64 antennas, it gives you 64 users that can be multiplexed at the same time, or 64 layers that you can transmit at the same time, provided that you find the optimum configuration of the ports and you have enough degrees of freedom in the fluid you have around your circle of your phone, in this fluid ring that you can imagine here. You can be playing with the position of the liquid, metallic liquid, until you find the optimal location for your receiver. So this is the position in which you can multiplex users, and you can get ideally maximum capacity of this. So if we go to the capacity discussions we have today, you see this paper is in April 2024 of the group of Professor Zhang. They are already talking about this capacity, and the capacity, you know exactly what we are seeing here. We have the covariance matrix, we have the log definition, we have the 1 plus SNR definition. But what we see here is that this capacity has many freedom arguments, because there is now a square region that is called CT or CR, that is the transmitter and the receiver square regions, in which you can freely move your position of the antenna. So actually the H matrix is dependent on the positions of all the different transmit and receive antennas, because every one of them has the possibility of move around. So if you remember Emil picture with his area that is fixed, and how he was placing the different elements, is playing with this. And in fact, if you remember the question that he put, that he say, in fact, actually the location and the separation of the antennas depend on the distance. Exactly, depend on the distance, this optimum. So you can play with the liquid to modify the position of each one of these antenna elements to maybe get them closer or separated, because you can play with them. This capacity now is dependent on the position or the port of this antenna that are fluid, and give you these degrees of freedom. I'm sure Emil is excited to know that he has more degrees of freedoms to play, because actually this is what is giving to you the fluid antenna system concept. So now the question is to play with it, and to play with it is a complex process. Is based on the presentation of Giuseppe, that is more about the scheduling and how you manage to allocate resources, allocate ports and resources into this. And we call about multiple access slow or fast, depending, as typically we call about slow fading or fast fading. It means how fast you are with respect to the symbol period, right? So in case you are working with average SNR in long term and several symbols, we call about slow fully antenna multiple access. If we are talking about energy, we are talking about fast. And here I will go to some results about what we have in the state of the art. Basically fast, but you have several people working on the topic. All of them, they are recent papers. And basically what we are seeing is that the fluid antenna system are allowing you not to suffer these deep fades that we are experiencing, and even we cannot overcome with maximum rate combining. You can get actually a better analysis of it thanks to the mobility of the metallics you have on top of the antenna. If we see also, which is the performance on average rate or zoom rate, comparing with very simple statistics, we have some paper recent in Communication Letters about fluid antenna systems from K-Kit again, in which we see how a traditional antenna is outperformed in the moment in which we give this degree of freedom. So it's in the same line as was explained by Emil. Is in fact confirming what Emil was saying, that actually is you are able to increase the degrees of freedoms and you can pack in MIMO way, and this is the last figure, the 2x2 figure, you can actually separate from this limitation on the sound capacity, and you can keep this linear row with respect to the frequency. And the last results on the state of the art are based on how to select the port, which is in fact the complexity now. And the people is doing in different approaches. I am putting here an interesting paper that is also merging artificial intelligence and systems of reinforcement learning to be able to iteratively in different training episodes to learn which is the configuration optimal for a different number of users that are being placed in a MIMO setup, and they have to choose which is the port you are going to use in this scenario. So this is a simple result, but that shows us that there is convergence and that there are also possibilities of making this port selection in a fast manner through artificial intelligence. This is not the only solution. I'm sure the guys that are the theory capacity guys, as Giuseppe and Emil, will be able to formulate also mathematically this and be able to find the convex optimization on this process. So I would like to finish already, not to overpass too much the time for the discussion and the panel, to go about the challenges and which are the topics of research that we have today. Well, there is of course the complexity of the antenna. This manufacturing the antenna is complex. The good point is that we can make it with 3D printers, not only the liquid, but also the metallical chambers and the radiator. So we have some people on the antenna domain that are progressing well. Then we have the problem of the material as such, you know, mercurium and so on and so forth. They have incompatibilities with other metals. So how to encapsulate it, how to make compatibility of materials, how to guarantee the durability of these metallics that is moving, the resistance, the degradation of it, and so on and so forth, is something to be checked. Also, the power consumption related to the control of the liquid, the fluid antenna system requires some energy to be placed into the mobility of the fluid. So this control and stability is also one of the challenges. And the integration with existing technologies and standard is, of course, a new problem that we have to identify, because, as I said before, there is not the same procedures for channel state information. What you have to do is just to find the optimum port for your received signal. So I would say that I can play 12 different PhDs on the topic that I put here, on dynamics and fluid antenna systems, on materials and fluid selection, on reconfigurability and antenna design, on the integration of this, on control of the fluids, on all the part related to the power management. The part related to environmental adaptability is important because of the materials that we are going to use. And then if we go to technologies, stability, prototyping, testing, and performance optimization are also topics that are of interest and that are research opportunities for all of you. And that's all. I will just conclude saying that it's an early stage technology, the fluid antenna systems. It gives some clues that can be a simplified way of enhanced capacity, adapting more users and easing the optimization and the procedures of transmission, recorders, and so on in the massive MIMO scenario. We have to learn how to pack it well and how to adapt it well and how to control it well, because it is still, as I said, in early stage phases. And well, why not? Artificial intelligence can be a way to learn and to be fast in the decision making in a way that we can make not only a system that has promise, but also is feasible for the integration on standards. And that's all from my side. Thank you for your attention. And I think, exceeding a little bit of time, but not so much, Martin.
Thank you very much, Jose, for this interesting insight on fluid antennas. That was very interesting indeed. And it seems to me that this connects nicely to the presentation of Emil, because we have learned that for point-to-point MIMO, the degrees of freedom, so the channel rank, depend on the position of the antennas in a very sensitive way. So
yeah.
Do you think the fluid antennas could help in this respect?
It should be in this direction. In fact, in the discussion we have now, as Emil is pointing in his presentation, the two concepts are related. And they say we need to be able to dynamically change the position of the antennas because they depend on the distance from base station to user. So there is a D in the equations of Emil. This distance affects the optimum position of the transmitters. And this requires that you are able to modify the antenna on demand, right? So this graph I have on capacity that I put the 2x2 is a system in which is a dual polar system in which the antenna ports, they can move it and they can increase the capacity as Emil was saying it would happen. Yeah.
Right. Okay, thanks again. Now moving on, the next presentation will be given by myself, actually. So a few words on my background. I've been working on the topic of MIMO for more than 20 years, starting with my PhD in 2003, where I worked on multi-user beamforming. And since then, my main research interest has been in the area of signal processing for wireless communications and networking, with a special focus on resource management. And since 2013, I am with Huawei's Munich Research Center. And within the 1.6G association, I'm currently responsible for the work item Next Generation MIMO. And in my presentation, I will give a brief overview on this work item. And I will also talk about a few principles related to multi-user strategies for user-centric cell-free MIMO. Okay, so first, everybody agrees that MIMO is a cornerstone technology for 6G and beyond. And our work item aims to gain a better understanding of some new emerging MIMO technologies. And this currently includes holographic MIMO and intelligent metasurfaces, integrated sensing and communications, also AI and machine learning, as well as new architectures, especially user-centric cell-free MIMO, also known as distributed MIMO or DMIMO, as illustrated on the right-hand side. You see here we have a distribution of radio units. So this is the same usual architecture that has already been presented by Giuseppe in his first presentation. And this then can be enhanced by some intelligent metasurfaces. So these are the new technologies that we expect for 6G, but we also want to take a fresh look at some old MIMO results, because with these new technologies and the new architecture, there also comes new types of resource constraint, for example, as also pointed out by Giuseppe, like fronthaul constraint, computing constraints, etc. Also, there is the issue of coherent joint transmission under realistic time frequency synchronization, which is possibly IP-based. And then we have the need for flexible association of UEs with radio units, so-called clustering. So we need to dynamically route the fronthaul traffic, and we need to take care of the resource allocation in such a distributed system. So in effect, we need to move towards distributed, flexible, and efficient multiple access based on MIMO networks. And in this context, let's have a look at the multi-user transmission over coupled MIMO channels. So the utilities of the K users are coupled by mutual interference and also by the limited resources. So we have, in fact, a multi-objective optimization problem over the achievable region, which illustrated on the right-hand side. And by the way, this is not just a simple illustration. This is an actual achievable region that we computed for a multiple input, single output, multi-user channel with linear precoding. Because linear precoding is the current focus of our MIMO processing, because with many antennas, with massive MIMO, this is nearly optimal for systems, especially if we also add this scheduling dimension. So now in this context, we can ask for the optimal transmission strategy for a cell-free downlink. So do the same conclusions hold as for the cellular case? Because this multi-user MIMO topic is quite old. It has a long history for 20 years. So what do we need? How do we need to take care of these new constraints? For example, for the scheduling. At the right-hand side, you see two examples for scheduling, depending on the user priorities, which are represented by these weighting factor here on the top. In the top figure, it is W1, which defines the operating point on the boundary of the feasible set. And in the top figure, you see that both users are active simultaneously. But it can also happen that only one user is active, as illustrated in the bottom figure. The single user transmission is optimal. So we have the dimension of power allocation and scheduling, and for our current research, this is the same. So we do power allocation over the feasible region, and in some cases, this leads to an operating point where only a few users are active simultaneously. And then, as an additional degree of freedom, we have the problem of clustering. So this is adding a new dimension to the problem, and I'm going to talk about this later. So the scheduling problem actually is not just the scheduling over resource blocks, but here in a more general sense, we ask the question how to select, how to pre-code and distribute the data streams over multiple users and possibly multiple MIMO layers, also subbands, time slots, and radio unit clusters. And since the infrastructure is costly, we will possibly have more active UEs layers than antennas. And here we support the view of Giuseppe from the first talk, that the common assumption M greater K, so that we have more antennas than users, may not apply, because we have many spatial, or might have many spatial layers in the system, but only a few of them are scheduled at any given time. And it is very important to sort out the channels that have bad channel realizations by appropriate scheduling. That means for each block fading channel realization, we need to solve a scheduling problem, which is essentially, for example, the weighted sum rate maximization problem, which is illustrated on the right-hand side. Here again, you see the achievable rate region, and depending on the user priorities, we have different scheduling decisions. So either only one user is active or several users are active simultaneously. And this depends on several factors. For example, for single transmission antennas, so the conventional case, it is always optimal to serve one user at any given time. But by adding MIMO dimension, this conclusions does not hold anymore, because with MIMO we can do spatial multiplexing or SDMA. And if we have orthogonal channels, then this is always the optimal case anyway. But how to deal with the intermediate case, so where we have a medium SNR regime and semi-orthogonal channels. So in this case, the rate region with linear precoding is non-convex, and this weighted sum rate problem is quite complicated, as has already been emphasized by Giuseppe before. And over time, so over time, we can achieve proportional fairness by solving such a weighted sum rate problem for every channel realization. And these are some classical references where this has been developed. And the weights, they depend on the past data rates, for example, by a moving average window, and then over the average rates, we can achieve proportional fairness. And the CSI can be obtained, for example, by uplink channel sounding and by exploiting the uplink downlink reciprocity. But here I would like to emphasize that it's still not clear how to obtain this CSI knowledge in a distributed system, such as cell-free system. So this, in our view, is still an open issue. And then we have analyzed some algorithms for achieving or for solving this weighted sum rate problem. One very popular algorithm is the weighted MMSE algorithm. It converges to a stationary point of the weighted sum rate problem by iteratively updating transmit and receive filters. And we see on the right-hand side in the simulation that the performance depends heavily on the initialization. For example, you see here the green curve on the bottom. This is the transmit matched filter initialization, and this performs bad for high SNR channels. So, but if we further iterate this weighted MMSE, so after a few iterations, so the black curve, this is one iteration, the blue curve above, this is two iterations, and then already with 3 iterations, we are coming already quite close to the optimum. And the optimum here, we don't know, but we have plotted the upper bound, which is the actual capacity of the system that can be achieved by dirty paper coding. And you see that with only a few iterations, so with 10 iterations, we are already quite close to this upper bound, which cannot be achieved. So there's not much room to further improvement. And and then we also have compared this result, for example, with greedy strategies, which have been proposed in the past. This is reference 3. So they use a greedy selection strategy with partial orthogonalization of the users and layers. And this depends a bit on the type of channels. So here we only use Gaussian random channels, and also in the literature only such simple channels are being used. But our first impression is that also the greedy strategies are quite competitive. So they achieve a similar performance, and also complexity seems to be linear. But as I said, we think that this still needs to be evaluated with more realistic channel models and also actual system constraints. So what about these results under new system constraints in a cell-free MIMO context? So we believe that there are still some open questions in this area. And as motivated in the beginning, we also want to look at the clustering problem. So what are the optimal clusters in a system? This is known as user-centricity. Each UE is served flexibly by a cluster of radio units, as illustrated on the right-hand side. And the cluster selection has impact on first the multi-user interference, and thus the precoding and scheduling, and also on the consumption of limited resources. So in this case, we assume that each radio unit has limited resources. So that can be fronthaul load, that can be transmit power, for example. And these clusters can also overlap. So now a very interesting question is, can we optimize this jointly? So the clustering, the downlink precoding, and also the power allocation and scheduling. If we approach this problem directly for the downlink, then we find that this is a mixed integer nonlinear optimization problem, and the discrete search space increases exponentially with the number of UEs. because all the UEs are coupled. So that means that the choice of one UE's cluster has a direct impact on the interference and therefore on the choice of another UE's clusters. So the clustering optimization is coupled. And that's why the complexity explodes, even for a moderately sized system. It's intractable. But there's a different approach, which is based on uplink-downlink duality. Because in the dual domain, it turns out that the search complexity scales only linearly in the number of UEs. And this has been shown in a recent publication by us. And to explain this result, I need to talk a bit about uplink-downlink duality. And also Giuseppe Caire has gave a brief introduction at the beginning. So what is this about? So this is exploiting the fact that for many downlink multi-user MIMO problem, we have the problem that certain optimization variables, for example, the precoders or the scheduling, the clustering, leads to a coupled problem, which is difficult to solve. But for many problems, it is easier to solve the Lagrangian dual problem instead. And this has the advantage that certain optimization variables decouple, which enables more efficient algorithms. And the dual problem has a similar structure as the uplink, and that's why it is called uplink-downlink duality, even though here we are not talking about the true uplink, but a virtual uplink that we used for optimization, so a proxy only. So the conventional uplink-downlink duality, so this holds under some power constraint. And here I want to emphasize that Giuseppe Caire, he has been one of the pioneers in this area. So he has made a very large impact on this very important result, which eventually led to the characterization of the downlink capacity region in 2007. So in a simplified way, we can say that certain rates are achieved in the downlink if and only if the same rates are achievable in the uplink. And this holds for a sum power constraint. So in both cases, we have the same sum power. And what is more is that the optimal downlink precoders are scaled versions of the optimal uplink combiners. And this is very convenient because now we can solve the problem in the downlink, and then we can directly we can solve it in the uplink, and then we can directly transfer this result in the downlink to the downlink. And this result was extended to a duality under per antenna and TRP power constraints. And this is now very relevant in the context of cell-free, because here we have that each individual TRP is constrained in terms of resources and also power. And in this case, it has been shown by reference 4 that we need to introduce an additional variable, a Lagrange variable, which is the noise powers of the dual channel. So these variables are a priori unknown, but it can be shown that also under such per antenna power constraints, both uplink and downlink have the same achievable region if we take care of these variables. If they scale them properly, then we can make sure that in the downlink, the TRP power constraints or the antenna power constraints are being obeyed. So what we need to do is we just need to run an additional outer iteration over our optimization problem to appropriately scale the dual noise powers NM. And since this equality holds under rate or SNR equality, it is quite obvious that in order to decrease certain antenna powers, what we need to do, we need to increase the value of this dual variable. And this is illustrated on the right-hand side. So on the bottom line, you see this dual variable. And then in the middle row, you see the per antenna powers. And on top, it's just the SNR, just to prove that both uplink and downlink have the same SNR, which is normalized. And then you can observe how we tweak these Lagrange variables, and the effect is that we can equalize the downlink per antenna powers. Okay, this allows us to run some simulations for jointly optimizing precoders, clusters, and the power allocation in the dual domain. And yeah, the cluster selection, this is still a discrete optimization problem, but the selection complexity scales linearly in the number of UEs. And this is a huge advantage. And it allows us to simulate large-scale systems with many users. So here we have 120 users, 2 different scenarios. One scenario where the users are evenly distributed, and another one where we have a hotspot scenario where many users are clustered around one TRP. And yeah, some interesting questions. Okay, first, I need to say that we focus on the power minimization problem. So the problem is we minimize the maximal antenna power subject to SNR constraint. This is sort of the inverse problem of the throughput maximization problem. And this is currently under preparation. And in this context, some interesting questions are, first, yeah, what is the benefit of optimal clustering compared to heuristic solutions that have been proposed in the past? And second, what is the loss compared to the case where per antenna power constraints are ignored and the optimization is simply based on the less restrictive assumption of a sum power constraint? And these results you see here. So here is a comparison. First, for the evenly distributed UEs, we observe first, so these are the per TRP powers. And this is the CDF. And what you see here, that we can balance the per TRP powers by the proposed algorithms. And this is compared to the case where we do heuristic clustering just based on the largest channel norm. So that's the gap between the green curve and the magenta curve. This is around 1.5 dB. This is what we can gain by doing the clustering in an optimal way compared to the heuristics. And then we address also the second question, what can we gain compared to the sum power optimization? Here we also gain around 1.5 dB. This is a comparison between the green and the red dotted curve. Yeah, so you see when we optimize the system with respect to some power, then many antennas have much less powers. But there are also some antennas which have much power, and this is creating a bottleneck because then we need to rescale everything. Yeah, and also here we have a gap of 1.5 dB. So here one could say, okay, this loss is not so that large, so we could also use the sum power constraint optimization. But this is an evenly distributed scenario. What about the clustering, the hotspot scenario, where we have many UEs clustered around one TRP? In this case, one could expect that this TRP would become the bottleneck in terms of TRP power. And then for this scenario, it is true that the gap between the sum power constraint optimization and the per TRP optimization becomes larger. This is as expected, but maybe not that large as one might think. So it's only 2.3 dB. And this explanation for this is that this, so first the TRPs with excessive TX power are avoided or can be avoided to a certain extent by reallocating some UEs to neighboring TPs. That's what the algorithm does implicitly. But this strategy, of course, has its limits as the increased path loss has also a detrimental effect, which is taken into account. Okay, this was a brief overview of what we are doing in our 16G work item, Next Generation MIMO. So we aim to increase our understanding of the implementations of Next Generation MIMO technologies. And this is not limited at all to the topics discussed here. We have other MIMO-related topics like risk enhancement, integrated sensing and communication, NTN, which are being studied in the context of this work item. And we are always open for new members. Yeah, there are some remaining challenges from our point of view, and here are just a few examples. I mentioned the clustering problem, but also there's a problem. What are the new challenges for hardware implementation? If the trend is towards more antennas, higher frequencies, and higher bandwidths, then we are getting new kinds of problem like nonlinear power amplifiers, low resolution ADC or DAC, hybrid beamforming with RIS, and so on. And also the CSI acquisition is of course a large challenge. So we need possibly transceiver designs under perfect CSI. And we think that, for example, the team MMSE approach proposed by Lorenzo Miretti in reference 2, that could be quite interesting path to go. And finally, also next generation distributed grant-free access. So what I presented here, that was multiple access under the assumption that everything is scheduled, but for grant-free access, there are some exciting new results on unsourced random access. And this is also driven by Giuseppe Caire in this reference 3. Okay, that concludes my talk. Thanks so much. And next we will have our panel discussion. Okay, I don't know if there are any questions in the Q&A area on my presentation, but I can also I will try to deal with that later. I will stay a bit in this webinar to answer this. Yeah, we only have 10 minutes left, so let's use this time to have a discussion among the panelists. So yeah, let's start the discussion with maybe. Okay, for example, for 6G, the ISAC, the integrated sensing and communication, this is a hot topic. So my question would be, can the 6G MIMO technology also be used for sensing and localization? And what are the key issues here that we would need to address? So are there any comments, any views on this?
I guess I can start saying something. So I think we see how the MIMO technology is sort of converging towards something that can be a really good sensing system as well. So I mean, in radar, the digital arrays is really military grade things, while it's sort of more phased array kind of things that I've been using for civilian radar systems. So it's kind of a capable thing, particularly if you're moving up in frequency as well. We are going to build MIMO arrays that are really capable of sensing features as well. Then when you have network slicing as a possibility of reconfiguring your 6G network or 5G network depending on use cases, then this seems like a logical kind of slice as well to have these sensing features. Then the question would be, is there a market? Can anyone pay for wanting these kind of services or requesting it from telecom operators? So there's a reason to provide them, but I think there's big opportunities from the technology side, at least.
So maybe I could add that ISAC is, of course, is giving to you this context awareness and the capacities of seeing things that you cannot see, but also is giving the opportunity for communication to improvement. Communication assisted sensing is one of the keys. As soon as you know which is the channel, as soon as you know which is the characteristics of your surroundings, in a dynamic manner that you can see targets and things occurring, you can adapt your transmitter and precoders to make the most of your communication channel. And this is something that we already saw in the literature, that ISAC can improve or can boost the capacity of 6G, which is important. And there, of course, the massive MIMO give you these additional sampling capacities to make your vision or your context awareness more precise.
Yeah, absolutely. Maybe I can also add one word here, is that at the moment, of course, it is still quite undefined what it will be really 6G technology, right? Because there was an initial infatuation for very, very high frequencies, terahertz, sub-terahertz. Then it seems that at least industry and somehow as a consequence also the research has folded back to more this kind of intermediate frequencies that are even in between, say, 7 and whatever 24. There's a FR3, which is not even millimeter waves. So and also in terms of topologies, is going to be mega massive MIMO, is going to be distributed, cell-free. I had the impression that one thing that maybe some interesting consideration is that at least for situations like campus network, super dense deployments, where you really have a lot of infrastructure all around, like say self-free distributed, something like that, the network essentially can operate as a big RF scanner. So when you go to an airport, basically you are in between a giant transmit antenna and a giant receive antennas, and basically they scan your body. But now imagine that you have antenna arrays transmitting and receiving without even involving the users, because users UEs are they follow different rules, but and different type of market dynamics and scale economy. But if you have an antenna array every 10 meters, and some of them transmit, some of them receive, even on small slots, it could be dedicated. It could be maybe some radio unit is idle at some point that acts as a sensor, something like this. I think that this is a little bit like giving a sort of tomographic imaging of the environment, which goes well beyond radar. When people look at radar, it's basically a problem of detection and estimation. Detection, the target is there, not there, and estimation of these parameters like the typical delay, Doppler, angle of arrival, etc. But this is military radar, and also in a certain sense automotive radar to some extent. But RF scanning or RF imaging is very different, where people who do imaging are not interested in distinguishing clutter targets from clutter. Everything is the image, right? You want to produce an image, and then maybe after you have this RF imaging, one can run inference on that, like, for example, recognizing signatures for, I don't know, pedestrians, cars, vehicles, and stuff like that. I think that there is a lot to learn from the RF imaging community. They have very sophisticated approaches that are quite not the same as used in radio localization, data detection, channel estimation, and even radar processing. I see it's a different community, and maybe there is something to learn there, and it could be an interesting direction for research for all the PhD students that are following this presentation. I think that there is a potential there to put together two areas that are still not completely fused.
Yeah, it seems that such MIMO enhancement also depend crucially on which frequency bands are being used in 6G, right?
Yeah, the role of the frequency is, I don't think it's really crucial. Is the role of the bandwidths involved, right? Because at the end, we want to have enough bandwidth in order to be able to have a good resolution in terms of delay. And of course, this is somehow also has to do with the frequency, because the bandwidth is available at certain frequencies, not available at other frequencies. But delay resolution is not the only thing. That there is angle resolution, and many times, when one does imaging in a multidimensional way, sometimes you can get resolution. A typical example, two targets are not separable because the delay is less than the delay difference is less than the the inverse of the bandwidth and things like this. But this is true only if you have a one beam and two targets on the same line of sight. If you have an imaging from all the places and you have many angles, you can resolve them very well. So this concept has to have to be reconsidered also to some extent.
Yeah, right. I agree. Now here comes an interesting question from the audience. What is your view on, and this goes to all the panelists actually, what is your view on holographic MIMO? Do you expect any room for large capacity gains? Because I mean, I fully support this question because infrastructure is always costly. Is it really worth the cost?
So I think from to the extent I've understood, so holographic MIMO would then mean having shorter antenna spacing than lambda/2, and of course there's all kind of hardware issues with the mutual coupling effects that will appear there. But even if those effects are dealt with, no, it's from the degrees of freedom perspective, you don't gain anything from having this smaller spacings. You could potentially gain a little bit in SNR, just as oversampling can allow you to do some SNR boost or something like this when it comes to time domain oversampling. But no, it doesn't seem from that perspective. So I would rather go for the opposite thing, having sparse arrays that are well spread out, but keeping the number of antennas a bit more manageable than what I was talking about in my seminar.
Yeah, that's an interesting perspective. Yeah, unfortunately, we have already reached the end of our time. I would love to discuss all these things further, but yeah, maybe if there are questions that couldn't be answered today, yeah, this is to the audience. So feel free to send me an email, and then we will try to give an answer even after this event. So unfortunately, we have reached the end of our 8th open lecture on next generation MIMO. So many thanks to all participants for interesting questions and good discussions. And yeah, special thanks to our guest speakers, Giuseppe Caire, Emil Björnsson, and Jose Francisco Montserrat del Rio. Thank you very much for your excellent presentations. I very much like it. So very much indeed. And finally, I would like to draw everybody's attention to an event that is going to be organized by the 16G Association in September. So this is the 16G Summit, which will take place in Valencia. And I learned that the agenda is already out, so you can check the website. Yeah, so that's it from my side. Thank you very much, all of you. And I think we can close the event.
Okay. Thank you.
Thank you. Goodbye.
Thank you very much.
Bye.
Bye.